Good day, my name is Mohammed Zidan, and today me and my group mates will be presenting on about the adaptive cruise control system for our second assignment for the ACI module. Here are our group mates with our respective student IDs, and I shall now be passing this on to the first presenter.
So, what is an ACC? ACC, also known as Adaptive Cruise Control, is a system that allows a vehicle to maintain a safe distance away from the vehicle in front, all whilst keeping the car below the set speed limit without input from the driver. That is to say, if the car ahead of you slows down, the ACC system will slow your car down based on the speed of the car ahead. So, what are the required components in an adaptive cruise control system? Well, there are five main components that allow the system to function. The first is the radar sensor. It is considered to be the core component of the ACC system, and its function is to permanently monitor the road ahead of the car. If the sensor detects that the road ahead is clear, the ACC will maintain the speed set by the driver. If the sensor detects there is a car ahead, the ACC will set the vehicle's speed based on the car ahead. The controller is the next component and is considered to be the brain of the system. The controller collects the data sent by the sensors, interprets it, and sends the appropriate signals to the actuator, which we will touch on shortly. The display is also considered a core component as it allows the driver to keep track of the vital info such as the speed of the car, RPM of the car, and the status of the ACC, whether it is on or off. Moving on, we have the throttle pedal, which is a component that controls the amount of air and fuel being directed to the engine via the actuator. The throttle pedal is adjusted by the mechanical movement on the driver's foot. The last vital component of the ACC system is the actuator. Also known as the throttle body, it controls the speed of the car based on the amount of fuel and air being fed to the engine. The orientation of the actuator is controlled either physically by the aforementioned throttle pedal or electronically by the controller of the ACC system. The signals sent from the controller is interpreted by the actuator and then is converted into mechanical movement. In this case, the reorientation of the throttle body.
Next, for question 3, the objective is to design a flowchart that outlines the steps involved in ACC control system. The current slide shows the flowchart that was designed where the activation of ACC until the output is as shown. Where first, when the ACC is activated and being used, it will first detect any obstacle that's in front of the vehicle. If there's no obstacle, then it will then activate the cruise control system, which sets the desired speed and transfers that information to the throttle actuator as it outputs as the car moving forward to that desired speed. If there's an obstacle detected, then the current speed will be reduced to the until to the point of brake, which is the drop of the brake actuator. Additionally, there will be a sensor at the near end of the output for both throttle and actuator and brake actuator, where its purpose is to continuously sense any obstacle that's in front of the car.
Moving on, we'll be taking a look at the block diagram for the ACC control system. Here, as you can see, there are 6 essential components for the system. You have the radar sensor, ACC unit, automatic cruise control unit, engine control module, brake control module, instrument cluster, and switches. Now we'll be taking a look at what each and one of these components do. Starting off with the radar sensor, as the name implies, it's a sensor which helps to detect incoming obstacles in front of the car, like other vehicles, maybe trees or people. From there, we also have the ACC unit, which is primary function is to process radar information and determine if a forward vehicle is present. It is also capable of controlling clearance between vehicles and target vehicle in front of it. Essentially, it helps to control the distance between the vehicle and another vehicle in front of it. Next, we have the engine control module. What it mainly does is it gathers information from the radar sensors and the ACC unit, which will then be used by it to control the vehicle speed by controlling the engine throttle. Now we also have the instrument cluster. The instrument cluster is basically the dash you see in front of the driver steering wheel. What it does mainly is it processes switch inputs from the cruise switches. It displays relevant information to the driver, like the speedometer and everything there. And it also helps to send info to the ACC or engine control module about the state of the car. One thing also helps to display text messages for like warnings or like sensor warnings or like low tire pressure warnings and whatnot to the driver. From there, we also have the switches, which help to toggle the ACC on or off, and the time gap control, where you can increase the time gap between the car in front of you and your car or decrease it. As mentioned, the switches will be used to on and off the ACC again, and the instrument cluster is the one that will process the information and send it over to the other module, the ACC control module. Engine control module and the ACC module. Lastly, we have the brake control module, which essentially determines the vehicle speed by braking, and also helps to decelerate the vehicle when requested by the system. That should be all from me. I'll now be moving on to the next person.
There are several challenges that can arise in adaptive cruise control system. Our first challenge is cutting in vehicles disrupting the ACC system. When a vehicle unexpectedly cuts into the lane, it can cause the ACC system to react unpredictably, potentially leading to unsafe situation. To solve this issue, we can implement sensor with a wider field of view. This sensor provides a broader detection range, allowing the system to anticipate and respond to sudden change in traffic more smoothly. This can involve using advanced radar and camera technologies that can detect vehicles in adjacent lane more effectively. The next challenge is sensor malfunctions. This can occur due to environmental factors or technical issues, compromising the ACC system reliability. Redundancy is key. By incorporating multiple sensors of the same type, the system can continue to function correctly even if one sensor fails. For instance, having multiple radar units can ensure that the backup is always available to provide the critical data needed. For the third challenge, ACC systems often struggle with complex traffic situations, such as heavy congestion, intersection, or mixed traffic type, where precise and rapid decision-making is crucial. To address this, we can integrate ACC with other driver assistance features like lane keeping assist and traffic sign recognition. These systems work together to provide a comprehensive understanding of the driving environment. For example, integrating lane keeping assistant ensure that the vehicle maintains its lane even in complex scenarios. The last challenge is the failure or incorrect identification of objects. This can result in the system misinterpreting harmless objects as threats or failing to recognize actual obstacles. The solution here is sensor fusion, utilizing multiple types of sensors such as radar, LiDAR, and cameras to cross-verify the data and improve object detection accuracy. This approach helps reduce false positive and negative, ensuring that the system responds appropriately to real threats. In conclusion, adaptive cruise control systems are a significant advancement in vehicle safety and automation, helping maintain safe distance and speed. Designing this system involves a deep knowledge of sensors, control system, and data processing, all of which are integral to automatic control and instrumentation. That is all from us. Thank you.